Okay, so this is E over m experiment. In this lab, we will find out the ratio of the charge to the mass of an electron. So, this is the apparatus we're going to use. These are called the Helmholtz coils, and it will have like the coils here, and then and these coils. When you turn on the current, the magnetic field is going to generate the magnetic field by this coil, and then the same thing by this coil, and the magnetic field is going to be the same direction. So you can add up two magnetic fields to get the total magnetic field in here, where the electrons receive the magnetic force, and then the electron gets deflected in the magnetic field. So let me start. So actually the experiment is E over m, so charge to mass ratio of electrons. So E is the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs, and then m is the mass of the electrons, 9.1 times 10 to the negative 31 kilograms. And then when you work on these numbers, then you're going to get this value. So this is the theoretically accepted value, and then we're going to check this value if we're going to get similar value in the experiment. So to start with, so this is the coil, and the current passing, the current I is passing with the radius A. So from the center to the x distance, the magnetic field B will be in the x component of the magnetic field B would be n mu naught I a square over 2 a square plus x square 3 half. I being the current, mu naught being the magnetic permeability, and n is the number of turns. So this is something we derived in the theoretical part. So we are using this in this experiment. So to start with the explanation here. So in the experiment, electrons acquire energy by the potential difference delta V. So E times delta V should be equals to the kinetic energy of the electrons. When you solve for V and velocity V, you're going to get 2 E times delta V over m square root. So remember, this delta V is not velocity, this delta V is the applied potential. So this V is the velocity of the electron beam. Now, the next thing is when the electrons move in a circular track, so necessary centripetal force that is required to go around the track is provided by the magnetic force. And the magnetic force equation is charge and then the cross product of velocity and magnetic field, and that should be equal to the centripetal force, which is mv square over r. So mv square over r, and then this is the velocity, and the magnetic field is 90 degree, and sine 90 here, and then I come up with this expression mv square over r equals to EVB. Now, so magnetic field in that point is given by this, but that we have two coils, and then both produce the magnetic field in the same direction, in x component and in x direction. So the total magnetic field will be this plus this, which is this. Now, so going back here, so mv over r, mv square over r should be EVV, and I get rid of velocity by multiplying 1 over v, and then I substitute the value of b here, and then because of the square root, we have to square on both sides. So when I square both sides, I got 2e delta v over m, and then m square over r square, and then everything is squared here, a raised to the power 4, and then a square plus x square 3 half becomes just raised to the power third. Now I'm going to multiply by r square over 2 delta v e, and then when I multiply on both sides, I got m over e in this side should be equals to e n square mu series square I square a4 r raised to the power second square of and a square. Remember the x, the value of x is a over 2 in our apparatus, so I'm going to substitute a over 2 and that's x squared over e squared over 4 raised to the power third, and then everything here 1 over e 2 delta v. So the next is, I further simplified. I got m over e equals to this value. When I further simplify, this e and e are gone. Now when I'm interested to get e over m, not m over e. So I'm going to flip over here e over m, and then this is going to go on the numerator, and that's going to come in the denominator. You can see I cancelled a raised to the 4 with the a raised to the 6 by leaving the a squared on the denominator. That denominator came here as a square in the numerator. So e over m equals to 2 delta v 5/4 raised to the power third a squared over whole thing raised to the power 2. So again, so n is number of turns on each Helmholtz coil. Mu naught is the permeability constant. I is the current through the Helmholtz coils. R is the radius of the electron beam. And delta V is the acceleration potential applied. And A is the radius of the Helmholtz coils. So once you have all these quantities, you can plug it in this equation, and you get the ratio of E to the M, and then you can compare with the theoretical value. I hope that's going to help. Thank you.